Okay, so our next speaker is Hsia, whose slides have just come up, and she will be talking to us about the experimental simulation of solar wind interaction with magnetic dipole fields above insulating surfaces.
Thank you. It's wonderful to be here. I'd like to share some experimental results from Colorado Boulder on the interaction between solar wind and magnetic dipole fields above insulating surfaces. And this is, of course, in relation to lunar magnetic anomalies. So I was going to skip this slide, but I saw like 3 people walk in. So I will, for these people, tell you what LMAs are again. These are regions of crustal magnetic field intensity. They range in size from about 0.1 to 1,000 nanoteslas, and, in strength, and in size from 1 to 100 kilometers. And they are, of course, correlated with swirl-shaped, high albedo markers on the surface, like the Reiner-Gelner swirl feature. And specifically, okay, I'm sure about this. All swirls have LMAs associated with them, but not all LMAs have swirls associated with them. And so this kind of leads us to wonder, what is the relationship between these local magnetic fields and space weathering caused by the solar wind? Now, the solar wind interaction with magnetic anomalies has been studied in a variety of ways, especially in situ observations, simulations, but not so much in the lab. There's a common principle that has been brought up, and that's the concept of surface charging. And what this is that ions, being heavy, are going to be less affected by the magnetic fields due to their large mass. And in contrast, electrons, which are smaller and lighter, are magnetized, and then they are diverted along magnetic field lines towards or away from certain regions in the LMA. And so what this means for us is that in certain regions, we expect there to be positive potential that builds up in what we call shielded regions. And actually, this has been indicated from observations in LMA regions themselves. We decided to study this phenomenon in the lab. And we used the device called the Colorado Solar Wind Experiment, which is a vacuum chamber that has, that has an ion source here on the left that creates a plasma and then accelerates it into the main experimental chamber here, where we have what we call simulated solar wind. And then we put our experimental setup in this chamber to interact with the simulated solar wind. Here is a simple experimental schematic that we use to investigate LMAs in the lab. The plasma comes in from the left, and it's incident on an insulating plate, and we place a simple dipole magnet right behind that insulating surface. Now, obviously, in the lab, we cannot replicate exactly everything that goes on in outer space, but what we can do is make sure that certain dimensionless parameters are kept constant between the 2 cases. So I'd like to bring your attention to 2 of these parameters that I've listed here, the electron gyro ratio and the ion gyro ratio. And these are indications of the behavior of these particles, electrons and ions, within a magnetic field and scaled towards the length scale of the moon and the lab. And as you can see, these factors match each other quite well. So it gives us confidence to believe in the results that I'm about to show you on the next slide. So to remind everyone, once again, we expect that ions being heavy are virtually going to ignore the magnetic fields and reach the surface. Let's see. Here. But electrons being much lighter are going to follow the field lines and are diverted away from what we call the shielded regions. And because of this, we expect there to be a positive charge buildup here in the shielded lobe regions. And that's exactly what we observe in the potential measurements that I'm showing to you on the right here. So you can see that for a variety of incoming ion solar wind energies, you do observe quite a large positive potential, especially close to the surface of the insulator. The z direction is the direction of the incoming beam, and the x direction is parallel to the insulating surface. But if you take a closer look, for instance, at high energies of, let's say, the 400 eV beam, you notice that even very, very close to the surface, the maximum potential that we managed to measure is only about 250 volts. Oh, no. Okay. There was a dotted line right here. Oh, it doesn't show. But let me explain what I mean a little bit better. So at low beam energies, you see that the maximum surface potential that we measure matches the incoming beam energy. So at 100 volts and 100 EV and a 200 EV beam, the surface potential also is about 100 and a 200 EV. But at higher beam energies, this trend falls off. And this is strange to us because we expect that in the absence of electrons near the surface, because remember they're shielded away, that at equilibrium, the surface potential needs to match the incoming beam energy, but it doesn't. So what accounts for this deviation? One possibility is that we were wrong about this initial assumption that electrons are shielded from this region, and they somehow got in. Fortunately, there is a way to test this, and we use what's called a Langmuir probe. A Langmuir probe helps us measure certain electron and ion characteristics in the vicinity of wherever the probe is placed in the experimental setup. So I've included a little bit of raw data here. Don't worry too much about it. But you can see that based on where I place this Langmuir probe, the raw current voltage sweeps are quite different from each other. And you can analyze this data and find that, yes, indeed, inside the shielded regions, we find electrons where electrons should not have been. Let me unpack this by going through the data in the graph on the left here for a bit. So, like I talked about earlier, if we looked at the black data points, we see that at low beam energies, the plasma potential follows the beam energy, but at high beam energies, this falls off. At the same time, at low beam energies, we find that there are virtually no electrons detected in the shielded region. But at high beam energies, suddenly the number of electrons in the shielded region increases very dramatically. So this suggests to us that, yes, indeed, electrons are responsible for lowering the potential in the shielded region, which then leads us to wonder, why are there electrons here to begin with? And there are three main possibilities. Firstly, that when high-energy ions impact the surface, they can create secondary electrons, and these go on to then lower the surface potential. Another possibility is that because of the high energies of the ions, large electric fields are being produced, and then these electric fields draw or pull electrons into the shielded regions. And finally, there could be collisions, somehow that manage to kick electrons into the forbidden regions. So let's go through each of these possibilities one by one and see if they make sense, starting with the secondary electrons. Once again, you need high-energy ions impacting the surface in order to create secondary electrons. However, if my target plate already has a potential associated with it, then the ion coming in has to overcome quite a large barrier before it manages to hit the surface. So if my surface is at 100 volts and my ion starts at 100 eV, so by the time the ion hits the surface, it has no more kinetic energy with which secondary electrons can be produced. We can use this knowledge to entirely eliminate secondary electrons and then see if the trend is still produced. And this is exactly what we did. We slowly increased the beam energy so that the plate always follows what the incoming beam energy is. And yet we still find that the trend kind of just falls off at high beam energies. So we've managed to eliminate secondary electrons as a source of, as the cause of lowering the potential in this forbidden region. So I have put the red. I'm sorry, this is weird. I've made the bubble red to say no to secondary electrons. let's move on to the electric field as a candidate. Now, this is an appealing theory because it fits the trend that we observe. At high beam energies, you expect high voltages and a high electric field, which means more electrons should be pulled into the, forbidden region. But unfortunately, this was not supported by simulations done. I've included an example here, done by one of my colleagues, that shows electron paths in an 800 eV beam. And as you can see, no electrons managed to reach the surface. So I've labeled electric field yellow as kind of like a maybe. And finally, collisions. We've done some experiments and we found that by increasing the chamber pressure, the surface potential actually continues to decrease. So this is interesting because chamber pressures are a measurement of the neutral particle density inside our experimental setup. And this means to us that somehow neutral particle collisions are involved in lowering the surface potential. At the same time, we know from measurements and from simulations that the electron density in the cusp region, which is here, of the magnet, is much higher than what it is compared to the rest of the chamber. This is a clue to us that the collisions between neutral particles and electrons are responsible for kicking electrons into the forbidden shielded region. So yes to collisions. And to summarize what I've just said, we've eliminated secondary electrons as a source of electrons in the shielded region. And so this means to us that it is the combination of the neutral particle and electron collisions, and as well as the strong electric field that helps to pull electrons into the forbidden shielded region. Oh no. Weird. One of my slides got missing. But what I mean to say is that I've shared with you some experimental results of the solar-wind interaction with the lunar magnetic anomalies. And we found that the surface potential is largely positive, but to a limit, and this is because electrons manage to enter the shielded region. But what does this mean on the lunar surface? How does this apply to everything we've talked about at today's conference and yesterday? Well, we know that there are going to be very, very high potentials on the surface of the moon. And in fact, we expect it to be higher than what we observe in the lab because A, the solar wind energy is much higher than what we used. And secondly, there's almost no collisions on the surface of the moon itself because of the super low pressures that we measure there. This has implications if we want to put boots or robots on the ground, and it's something to think about if we want to go in that direction. Right, so this means that, of course, if we want to know more, measurements on the surface, like everyone else was saying, totally necessary. Thank you for listening.
Okay, do we have questions for Hsia? Okay, I see Rick coming over to the mic. And don't worry about the slides, it was still great. You know,
yeah, like something was missing,
yeah,
I don't know.
That's fine.
Hi, I'm Rick Elphick from NASA Ames. That's really great work. It's great to see you guys doing this in the lab. It sounds like the thing that may be in the more immediate future, rather than boots on the ground, would be actually getting lower pressures inside the device in Colorado.
We are actually working on that right now. So we have a bunch of different plans. One is in modifying the way the beam comes out into the chamber, trying to shield that. We're trying to think of using different kinds of gases so that ionization is easier and results in fewer neutral particles, and also just adding more pumps. Mm-hmm. But because we've managed to isolate the effects of collisions that explain our results, we know that, well, there are basically no collisions in the moon, so we can predict what it's like on the moon itself.
That's true, but better, more measurements even at lower pressures, better vacuum, more pumps.
We're definitely working on that, yeah.
Looks like we have another question. Yep, plenty of time.
Hi, great talk. I was curious if you thought this process could modify the near-surface electric field in any significant way that
absolutely.
would affect dust process.
So that is so true. So actually in the slide that disappeared, I talked a little bit about the near-surface electric field and how that's going to be changing the number of ions that reach the surface, for instance, and then that kind of cascades all the way to dust movement and such.
Okay, cool. I also just want to note there's been 3 anomalies now in our PowerPoint presentations, not magnetic anomalies. There's been error. I had the material drop from my slide. Megan had material drop from her slide. And so I think I would recommend everyone go through the slides, because something is going wrong, because I had material lost.
Yeah.
Strange, yeah.
Yeah, so I think Maria has the slides on her machine in the speaker ready room, so if folks want to just click through, double check their slides look okay.
I made that mistake. I didn't check it all the way through, so do that.
No, but yours is just as great, even without that. Okay, so we have a discussion session scheduled. I'd still like to break at 10:45 so we can get back on track for people who are online. But does anyone have any other questions for Ian, Megan, Carly, or Hsia?
Do I still stand here alone?
Actually, yeah, that's a good question. Yeah, everyone should. So could Ian, Carly, Megan come up?